the second portion of lecture 3. So you can see that if you're applying a force on this line, it will start bowing out from one side and start forming a circle around this. So if you look at it under the microscope, under a very high magnification, um, if you continue to apply the stress, it will produce an unlimited number of dislocations. And then in the end, once you have completely um, filled the whole space with so many dislocations, then it will eventually shut down due to the stresses produced by the dislocation pileup. Okay, so you can see that, of course, I mean, these are stacking fault energy areas, and you can, and then some of these are also twins and so on. So these are different kinds of structures that you will find if you are doing a very, I mean, magnifying this material um, under an electron microscope. Okay, so these are some pictures that I have from the textbook. If you go look in the textbook, you will find the same things. Okay, so you can see that these are the dislocations lines. And if you have deformed the material and created more dislocations, you can see that they start moving with each other, and they will start canceling out each other or multiplying and things like that. So in half a micron, you see so many dislocations. So just imagine the amount of dislocation that you will find in an area that is 1 centimeter by 1 centimeter. So that's what the whole concept of 10 to the power 11 to 10 to the power 12 dislocations per centimeter square. So how do you find dislocations? You have to um, etch the material. I mean, you have to polish the material, you have to etch it, and you have to use what is called transmission electron microscopy in order to look at these dislocations. And you might be seeing them at an angle. So when you are doing that, this may be visible in one direction, but it may not be visible in another direction. Okay. So again, I had these are from the textbook, so I'm not going to go over them. So, and I think, so you can see that the slip systems in different materials are different. The preferred slip systems are different for proper deformation. And if you recall, we had what is called the critical resolve shear stress, which you need to exceed in order for you to start deforming a material. So I'm not, again, you can see that the strain hardening coefficient is also correlated to um, the stacking fault energy. So you can see that aluminum and iron will have very high stacking fault energies, whereas stainless steel, brass, etc. will have very low stacking fault energies. So again, you can see that. So I mean, this is just a, um, and we will go over that in some of our future classes. Okay, so I'm not going to go over them right now. I believe that um, these are some pictures from the previous, I mean from the textbook. So I just put them in there. Suppose you need to add them for any papers or any of your lab reports and things like that, you can use them. Okay, so that's all I have for this lecture, and I will see you in class today.